density matrix equals to your sum u with the previous t equals to t0 or some, this is t just t1 and u dagger, but the time difference is encoded in the unitary operations here. Okay. So now let's do a bit more, and that is some more characterization, and then slowly we'll enter various quantum noisy channels. So what so let's do some characterization. First of all, the trace of this matrix should be equals to 1 because it's a probability sum. So and the ultimate matrix I form. So I should get back the sum of these. I mean the trace of this particular matrix 1. So okay, so let's do a proof of this particular property. Is that we define some row, and that row is basically sum over I, pi, and the states psi I dagger, like this the outer product of the quantum state. So the trace of this row, by definition, it will be over some pi and the trace of this matrix, right? Sorry, and so by definition of the completeness, we know that this must be equals to 1, and then basically so then basically you have this because this is like a identity matrix, right? The outer product of the same unit vector is basically the identity matrix. And then basically they are complex unit vectors, so their outer product is equals to identity trace of that equals to this 1 basically. And then you have sum of the pi that is equals to the sum of probabilities equals to 1. So now suppose this kit psi, the second property is trace of the second property is this row must be a positive definite matrix and a positive semi-definite matrix. And why it is so? So let's take kit psi be some arbitrary state. Some arbitrary quantum states. So if it is some arbitrary quantum state, and then basically the product psi times the rho times psi, this is equals to sum over this psi, and let's define this row p, and this is as say p basically pi times say ai, outer product of ai and ai, okay, and psi. So this is here, and this is here, and I have defined rho as probability with some quantum state ai and ai. Okay. So this is how I have defined, because this particular psi is I free index free, so you can put inside like this, and then if I can do that, then this is equals to, I can write it as sum over pi as this is equivalently, I can write it as a product of the phi times ai. This is the same thing, right? This is the square of this. So a square of anything is basically non-negative quantity norm, right? It's a non-negative quantity, and probability of sum of the probabilities is equals to 1. That means it is greater than equals to 0. So because this cannot be less than 0, so this should be greater equals to 0. If and only if the inner product is 0, then it is 0. Other for any other values, this is greater than 0. Okay, so this is proven. So it's a basically positive PSD matrix, positive semi-definite matrix, right? So last week we have covered various matrix decomposition techniques, right? And definitely, if it is a PSD matrix, what straightforward comes in mind is the Cholesky decomposition. You can do many other decomposition, definitely the eigen decomposition, but this is very specialized for this kind of matrices that this can be decomposed as to lower triangular matrix. So because it's a complex matrix, so I can write it as LL star. So for this, this is applicable. Okay, I don't know whether it will give some advantage or not. That's a different thing, but this is applicable. Now, definitely the number of elements in L is roughly half of the element in rho, so you can minimize the complexity if you exploit the structure of L. Okay. So there is some alternate story, and that is since rho is basically positive, then its spectral decomposition. I can do the spectral decomposition through eigenvalue decomposition or something like that. So I can diagonalize this as rho equals to sum over j lambda j times this state vector j outer product with where this lambda j are they are the real numbers because this is a positive semi-definite matrix, of course, a Hermitian matrix. So if we look at the element of rho, they are typically Hermitian matrix, and that's why these eigenvalues are the real eigenvalues, and these eigenvalues are non-negative basically because the matrix itself, if it is like this is equivalent to lambda j. Eigenvalue of this particular matrix should be greater or equals to 0 as well. So you can prove this through Cayley-Hamiltonian theorem as well, or directly by just looking at the problem, you can show that. Also, we know that the trace of a matrix is the sum of eigenvalues, right? Sum over j lambda j. So if so, that means by trace property of because we just have learned that trace of rho equals to 1. So for this kind of setting, sum of lambda j equals to 1. So this is equivalent from the first characterization. These are equivalent. So these are equivalent. Um, this is the same principle. Okay. So that means what? There is a why I am showing the linear algebraic relations here. This is important um, because if I can represent the ensemble of a quantum system by probability and its states, right? If this is the ensemble of the representation of a quantum system, where we have the uh, basically uncertainty of the quantum system, right? I mean, we do not have a perfect description of the system. State is completely not known in that particular case. So every time you generate the quantum information, you have some associated probabilities of the realizations, that is pi psi I, if that is the representation of the quantum system. It is equivalent to say in the density matrix formulations that you can represent instead of the probability, you can represent by the eigenvalues and the associated eigenvector. This is same. This is also a valid representation, which is also an ensemble of state that describe describe its state with the density matrix rho. So this is an important density matrix. So this is an important comparison because now I can relate this, and how we can relate this is like this. Okay, let's look at an example. Suppose you start with certain quantum state and you design a quantum circuit, right? You apply certain gates, say Hadamard, 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 Hadamard. You apply multiple Hadamard gate. You apply multiple rotation gates, say control rotation, some phase rotation or theta. This is some arbitrary decomposition circuit that is basically representing uh, some algorithm. Okay, that is the operator U, because these all are individually unitary operators. So their tensor product as well as product is another unitary operator, and this is some U. Okay, and then after that you are doing the measurement, right? This is typically a quantum circuit for some problem. Okay, and what is your input state? Your input state is many Ket0 tensor product n, as many number of qubits you do. Suppose there are n number of qubits. So your initial state was the state 0 tensor product n, and you applied an algorithm. So this is an algorithm UA. An algorithm in quantum is just a design of an operator, perfect operator. If it is a full quantum algorithm, there is no classical thing. Okay, there is a question. Is there any limit how many ensemble of states a state can live in presence of noise? Is it infinite? Theoretically infinite. I should not comment. I'm not a theoretical person, but I mean information theory person. But in general, theoretically many. But it limits to certain numbers which we can permit. For example, as a quantum computer science student or a scholar or a scientist, I can say we typically you would say 10,000 experiments or a 1 lakh experiment in Qiskit or some software. Okay. So this is known as quantum sorts. Okay. So so you do 10,000 times and you allow your operators to, although we do a separate measurement scheme, but in general for the understanding I'm telling you that you are fine to say 100 such realizations. Okay, 100 realization of your some particular quantum state, and these 100 realizations you are defining with 100 qubits, for example. Okay, or even with less qubit you can also do. That's fine. I mean, in general, if it is 2 to the power n, n is the number of qubit, and this is the number of realization. So this will give you the number of basis states. Number of basis states. Say, for example, if you design a circuit with 3 qubits, Ket0, Ket0, and Ket0 as initial state. So this will generate all 000 to all 111. So these are all the realizations. Now the probabilities will change. And how many times you look at the probability? Say 1 lakh times, 10,000 times, or something, right? So that many realizations you can create. So now you can ask me that so definitely we started with this state, we applied some algorithm, and we reached to some other state, some ket psi, okay, at the output of this algorithm, which is still not measured, okay. And definitely I can see, because when I apply these quantum gates to a circuit physically in the actual hardware, so my system is interacting with the certain things which is coming from the environmental side. For example, pulse. We apply certain pulse signals to the superconducting chip, or we control annealer with basically thermodynamic change with the environment by heat exchange, or something we would do in a particular, or in a photonic quantum computer, you change the polarization of the photon or the number of photons, okay, by certain means, by laser beams or something, splitter, something like that. Okay. So in various quantum settings, you have various ways how you implement these gate operations or the operations that will perform that algorithm as a whole. Okay. And at the output, definitely the state, quantum state psi, has some inherent noise in the information that is in the probability. But when we do the measurement, there is a measuring device to do that, right? So we get for each basically Ket0 to say Ket111. These are the 8 state 1, 2, 3, 4, 5, 6, 7, 8. Okay, all 0 to all 1. Say the second state is 001 and so on up to the last state is basically 10110. So that is the state previous to this. So there are 8 such states, and you repeat the experiment, right? when you repeat the experiment, how many times this is repeated, 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 and that's gives you one histogram, right? So so this is the histogram you get, and from the histogram you try to retrieve your result that okay, these are the highly probable measurement basis from where you actually recover your information or the output of an algorithm. This is how it works. Now, what we are getting are some frequency, like the probabilities, right? Say P1, P2, P3, right? And your quantum state has some realizations of now your quantum state, because it is projected in this basis set like 0000001 and something, and you have the associated probabilities, right? But in fact, that is equivalent to your eigenvalues, eigenvalues lambda. And these eigenvalues are related to the physical quantity of the Hamiltonian operator, right? What you are looking for. So that means density matrix also gives the same thing. So there is no special about it. So if you can realize something with the probability distribution, it is same. It is same if you get the eigenvalues. Okay, or it is fine to have the probability distribution to comment on the eigenvalues. If you realize, if you can decompose it to the orthogonal basis set, that is the eigenbasis set or the eigenvectors. Okay, so with this there is a formal decomposition techniques, and let me write that particular decomposition called as made decomposition for general system. So and the theorem is something like that. This so suppose ket psi is pure state. Suppose ket psi is a pure state. Okay, there is no uncertainty of a composite quantum system. Composite quantum system A B. Okay, then A may be your quantum circuit, B may be the environment or something like that, or they can be any arbitrary two quantum systems, or I mean two systems. Then there exist orthonormal states. Orthonormal states, state IA. These are the orthonormal states for the system A, and similarly for system A. And orthonormal set IB for system B. System B can be environment or it can be a simple system B, such that um, you can represent your quantum state in the composite set of I, lambda I, IA, outer product of IB. And this is a spectral decomposition for composite system of AV. Okay, and I will not give the proof. If you just look at any standard quantum information theory book, this theorem is proven. I mean, you can see the proof. I'm just writing the theory. So here, lambda I, they are the real numbers, belongs to the real numbers. They are basically non-negative because the associated density matrix will be the positive semi-definite, and also the sum of lambda j square in this particular case over j spectrum will be equals to 1. These are known as the Schmidt coefficient. Schmidt coefficient. So in general, in classical communication theory, in classical signal processing theory, you have seen that. Okay, so there are questions. This is outer product. Okay. Not outer product. The left hand side is a Kate notation, right hand side is a matrix. Is that the case? Oh, then I have written something. Um, yeah, you're correct actually. So basically, this will be a outer product if and only if this is a matrix. Okay. So definitely, if it is a density matrix, this is the representation is correct. And as this is a pure state I denoted, so this will be the just this is something like this. So I have to check this one once again, whether this particular Smith decomposition um, is correct or not. So yeah, I hope they should be giving in terms of the density matrices or in terms of this the state representation. So this will be actually. Please let me rectify. Thank you for commenting. Um, this will be like this. Okay. So these are the eigenbasis product, eigenbasis representation. Thanks. Now, let's compare this equation with our classical noise analysis in the classical communication theory also, like because many of the people are from the engineering thing. So suppose basically you have a input X set of symbols, okay, and it is passing through some communication channel H or some channel H, and you are receiving some communication information in the classical setting as Y, and there is some additional noise coming from the picture environment W, right? This is the additive noise. So typically we write it as X H plus W. This is at your equation, right? And in certain algorithm, like for example, the MMSE equalizer and all, we have seen that you form a covariance matrix that is expectation of this Y Hermitian star. And from there, if you decompose this matrix, there are two metrics for the signal part and the noise part. And ultimately, if you decompose this R to via eigenvalue decomposition, so you see that this R has some eigen distribution like this. So basically, or you if you do the SVD, say for example, okay, so or EPT, whatever it is, so you get certain something like this. So basically, you can divide into two parts. First part, there will be both the signal component power plus noise power. That will be lambda I plus sigma W square dot 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 up to lambda 1, lambda 2, say lambda R plus sigma W square if this is a white noise. If it is a colored noise, it can vary. And then these all will be sigma W square. So this part is basically the noise component plus the eigenvalue component for the system part. And this is entirely the noise component power, right? So this is like the same thing we have seen like in the from the Smith decomposition as well here in the quantum system that you can denote with the both the system orthonormal basis A and B, but the overall basically sum of the eigenvalues lambda I square overall energy of the system sum will be equals to 1. Here these are the probabilities. Okay. Um, so now let's look at the quantum noise part, and then I'll show some examples, and then we'll take a break, and after that we'll come back again with the programming session. So okay, I am basically I'm not intended to go to this particular thing where you have uh, you have a system, quantum system Q, and it is interacting with the basically I should write in this way. So a quantum system for the density matrix representation is rho s, and it is interacting with the environment with this, and we write them as a whole composite system. So if this is the total, basically a composite system representation of both the quantum system and the environment, right? The density matrix representation. Then the evolution of rho c will be, the evolution will be basically u, rho s tensor product with rho e, and this is basically an assumption. This is not always the case. Then u dagger, and there are certain operations, because we want to minimize the effect of the environment. That's why we take the basically partial trace over the environment, and u rho s tensor product rho e and u dagger, and there are Krauss operator representation. So this is a separate ball game for in quantum communication. We will come back later sometime, not in this QT-03 course. Okay. So I'm going in the reverse side where there is a direct connection with the quantum computing circuit. Okay. So this is a, I mean, pretty much there are very different like communication theoretic approach for this problem, as well as if a system interact with this particular environment. So there are associated equations like the Master's equation or the Lindblad equation. So this is a separate branch of the thing. So I'm avoiding that part. Okay, so we'll come back because that will take a series of classes. So now let's come back to the noise part. So we'll specifically cover some noise here in this particular course, which are important. And Dr. Ritojit probably tomorrow will take some class, and he will demonstrate on various error mitigation, noise corrections technique. So this maybe he will use these examples there. So I'll not cover much in these practical things today. But from the general, because I'm taking the course on statistical inference, I'll show some examples on that angle. Okay, assuming that the theory is pretty much at least the basic part is known, or that can be taken from the material that I'll be sharing. Okay, so let's understand what is noise. So basically, let's define various types of noise. Okay, so one is the bit flip noise. So so bit flip noise is that some sort of noise which can do my ket0 to ket1 or ket1 to ket0. Okay, that vice versa it can do, and with probability, say with probability 1 minus p. So what do I say? I have a set of qubits, right? And there are some noise from the hardware side which are coming into the picture, and ultimately they are impacting my qubit state, and that qubit state is going from 0 to 1 or not. So for example, I started with a quantum state 0 0 1, whether it is becoming say 1 1 1. So that means there is a bit flip in 0 and 0. Okay, 2-bit flip has happened here. Okay, this is the case. So this kind of quantum channel or the error channel is called the bit flip channel. Okay, and there are associated two things, and let me define the part first, and then I'll come back. So there is a basically Krauss representation. Probably I introduced this term in QT-03, and that is called the Krauss operator representation. Uh, now E dagger, and we are Krauss operator. Yeah. So a quantum operation, let me define a quantum operation as epsilon. Okay. And that transform that input density matrix. So suppose you have an input density matrix rho, and it is transformed through some quantum operation because of noise or because of time evolution or something. And that particular operations I am denoting as epsilon. It's a functional mapping. Okay. So that quantum operations we are defining by E epsilon of rho, right? Or E of rho, whatever you say. Okay, this is a curly E notation. Okay, E of rho. So that is basically an operation on the density matrix rho, and it is defined by sum over k ek rho ek dagger, where ek are known as the Krauss operators. So there are details of the Krauss operator from the wild book you can look at, but I will just define one property of the Krauss operator. ek is basically, so these are important matrices for noise analysis. So ek is known as the Krauss operator, and its elements basically does the operations on the density matrices, satisfying there is a condition for this, that sum over k ek dagger ek equals to identity. So this is the condition for this Krauss operator. So this defines the completeness relation, and it ensures that the operation is trace preserving. That is the trace of your epsilon rho. This particular operation is basically trace over rho equals to 1. Okay, this is the condition for the Krauss operator. So this will help us to work on the product states, basically, or the composite state, where you have noise, effect of noise, and you want to basically analyze the impact. So say for example, this bit flip channel noise, what are the Krauss operators for that? So there are two Krauss operators. So one is E0 for the bit flip channel. E0 is the first one. E0 is defined as the probability with which basically the transition happens on the qubit 0 is basically square root 1 minus p. So what is happening here? Just 1 minute. These whiteboards often create problems. One minus p times the identity matrix I, and this is basically equals to 1 minus p 1001. Then E1 is the Krauss operator. Square root p is the associated, like the p is the probability of changing the state 1 to 0, and that you can do because it's a bit flip, so you can put a x gate here, and then basically the Krauss operator will be square root p times the poly x gate, that is 0 1 1 0. So then action of the channel is basically the bit flip channel. You can define as say bit flip channel, or the bit flip quantum operations on the state row can be defined as E0 row E0 dagger plus E1 row E1 dagger, right? And this will be basically equals to, from this definitions, you can also write it as 1 minus p times the matrix rho plus e x rho. Okay? So p is the probability. Okay. So because you have applied identity matrix here, so I just removed that part, because identity times any matrix is basically out. So you have only this part plus this part as your the channeling, basically the operation on the channel. Okay, if there is bit flip things happen. Okay, let's take an example to appreciate this idea a bit more. Suppose bit flip on gate 0. So let initial state rho equals to something like 0 0. This is your initial state. Okay, so 0 0 is what? 1 0 0 0. This is your so this is example. So 0 0 is basically 1 0 0 0, right? And that particular case, So this is the initial state rho. If I define rho in this way, okay. Then let's define the error channel BL, and that is also acting on 0, 0. Okay. So this will be 1 minus P times 0, 0 plus P times X times 0, 0 X, right? Because this is your rho. So this is your rho. And then since X on the ket 0 is basically ket 1, right? If you apply ket X on ket 0, you get ket 1. So basically, also you have X ket 0 times ket 0 X. So you can just represent this as ket 1, right? So so basically, this overall representation, we can write it as on the state 0, 0. If our density matrix is this one, then 1 minus P into the matrix 1, 0, 0, 0 plus P times 0, 0, 0, 1. So this is the outer product of 1, 1. Okay. So this is, if you get, then this is equals to your 1 minus P 0, 0 and P. And this is exactly at the initially when we were saying seeing this basically outer probability is basically transition matrix in the times the input state vectors. But in this particular case, you can see this is 1 minus P 0, 0 P, right? So this output state represents the qubit remaining in the state 0 with probability 1 minus P and flipping to gate 1 with probability P. So now you have an exercise and let me know the answer. Suppose your density matrix, you prepare rho as in the superposition state. Okay, this is your rho. Okay, and I'm giving you the values half of 1, 1, 1, 1. Can anyone tell me the final state for EBF? Take some time. I'm giving you 2 minutes time. Let me know the answer for this. Just apply the definition, and the probability is basically 1 minus P again to change plus state to minus state. Okay. This is a exercise for you, just to let me know what is the answer for this. So there will be a very short answer for this. Actually, I showed this in the linear algebra class as well in QT-02 probably, or yeah. So, but there it was something else with some quantum gates on measurement basis and some other things. But here it is in terms of the Krauss operator. No, answer is incorrect. Yes. So answer will be again plus state and minus state. You started and you reach the same state. So there will be no evolution of rho there, because plus state is an eigenstate of Pauli X gate. So if you apply Pauli X gate on a superposition state, it will not impact anything. This is an eigenstate of that system. It will repeat and repeat again the same answer. Okay, because it is an eigenstate. So If you create a density matrix with plus and plus, and if you do this quantum channel representation, ultimately you will go to the same state. Okay, this is a tricky question, and um, let's understand the phase flip channel now. So note that this phase flip channel is common both to classical and the quantum. Okay, so both the classical communication system or classical information theory and the quantum information theory has the same uh, bit error channel. That bit can be shifted from 0 to 1 and 1 to 0. But phase flip channel is very important, and this is very specific to quantum channel only for the quantum channel, dedicated to quantum channel. Is that the phase flip channel models an error whether there is a relative phase, whether there is a relative phase between gate 0 and gate 1. And this information is not there in classical information theory. This is very new. Okay. So so basically that means what I am saying is that gate 1 to minus gate 1. So there is no error in classical information theory that is taking this picture as an error channel 1 to minus 1. And let's take the probability that Kate1 which changes to minus Kate1 is P. This is the probability. Okay. So um, so the Krauss operators basically E0 is basically your square root 1 minus P, and E1 is basically this square root P times the Pauli G matrix. Okay, Pauli G matrix is a capital G, okay, Z matrix. So this is square root P times 1 minus 1 0 0. This is the matrix. So if these are the Krauss operators, then my channel can be written as this channel, or the quantum operations on rho can be written as E0 times the density, initial density matrix rho, E0 dagger plus E1 rho, E1 dagger, and that is equals to, here in this particular case, 1 minus P times rho plus P times this plus P times this G rho, G dagger. So G dagger equals to G actually. You can write dagger, but G dagger equals to G. Okay. So this is something which is unique and which is only present in quantum information theory, not in the classical part. This particular error. So this is unique in quantum noise analysis, that there might be phase changes, relative phase changes in basically the qubit information. And what is the physical notion is that? So classically you have 0 and 1, and they can change. Any noise can change 0 to 1 and 1 to 0. But 1 to minus 1, this basically is physically, it doesn't mean anything, because how you created 0 with some high voltage, this is some low voltage, but what is the phase information there with this preparation? Error is not captured. But in the Ket0 and Ket1, so because you are interacting with is a vector quantity, and obviously you can always denote this vector as e to the power some I phi times the vector Ket psi, and this phi is important here as a phase, right? Phase information, and this phi can be impacted by the hardware. Okay, so. Uh, let's do an example now. And this example is important. I mean, many times I repeat this story, and this is basically, suppose rho is again this 0 0. Okay, somebody calculate this and let me know what is my evolved state after this impact of this channel. Calculate somebody. I have given the formula here, and value of z is basically 1, 0, 0, minus 1. Just a matrix vector product. So it's a very simple thing, a simple matrix. And let me know what's the answer. Yes. So someone answered. And the answer is again, you started with the density matrix 0, 0, and you reach the same after the impact of channel 0, 0. So this is your row, right? So that's why computational basis set is so important. So because 0 is an eigenvector. 0 is an, okay, let me write here. 0 is an eigenvector of the Pauli matrix G. So if something is Pauli matrix, so basically if you do the sigma z measurement, right? If you do the sigma z measurement, because computational basis is an eigenvector of this matrix G, the repeated measurement of that will not impact in the result, right? So because if it is not eigenstate, so every time it will have a different realization, and the impact of channel will change the state repeatedly, right? Because you will come up with every different state. So that's why in Qiskit, you will see you are measuring on the state 0 using the Pauli G basis measurement. So every time you do measurement, but impact of the noise is basically negligible. If it is phase basically phase error, phase flip error. Okay, so the phase flip error is minimized. So this K1 to minus K1 is minimized using this measurement on the computational basis. So this is the intuition for that. I mean, there might be many other regions, but this is one intuition from the theoretical side. Okay, so I'm taking a break of 5 minutes and I'll come back again.